Welcome to AI Paper Swap. Today we're diving straight into Terence Tao's August 2026 paper, Mathematics in the Age of AI.
Yeah, which is based on his big International Congress of Mathematicians lecture.
Exactly. And the core thesis you need to know right off the bat is this. We basically have to stop debating whether AI can do research-level math and start preparing for a massive paradigm shift.
Right, going from what he calls proof scarcity to, proof abundance.
Yeah, Tao warns of this impending era of proof indigestion. Basically, AI generating these formally verified but completely incomprehensible proofs.
Which is wild because it threatens to break the historical alignment between solving mathematical problems and, actually advancing human understanding.
So if you're working in ML or AI research, this paper is just a massive wake-up call.
Oh, absolutely.
Because it shows exactly what happens when our systems, hyper-optimize for the wrong metrics. But to understand why a Fields medalist is sounding the alarm, we really have to look at the baseline assumption he forces us to accept here.
Right, what he calls his working hypothesis. Instead of arguing about current LLM limitations, which, let's be honest, we all do way too much, Tao asks us to just assume that AI tools will soon be fully capable of research-level math.
Yeah, and not just capable, but incredibly cheap.
Exactly. He cites that first proof project from May 2026.
Oh yeah, that was really fascinating.
Right. The evaluators took frontier AI models and fed them 10 genuinely novel, unpublished research problems.
Like completely out of the training distribution.
Yes. They weren't scraped from Arxiv or GitHub. And 7 out of the 10 received passing grades.
Wow.
And the compute costs were just tens to hundreds of dollars per problem.
$10 to solve a novel math problem. It changes the entire economy of research.
Stop and think about the economics of that. When compute gets that cheap and that effective, the dam just breaks.
It reminds me of the historical prologue in the paper. Tao connects this to the foundational crisis of mathematics from 1900 to 1930.
Right, with Russell's paradox and Gödel's incompleteness theorems.
Yeah. Like the famous Barber paradox. It broke the absolute certainty of logic. And then Gödel showing that complex systems will have true statements that literally cannot be proven.
The foundation of math basically shattered back then.
But there's a really critical difference here that Tao points out. That crisis in the 1920s, that was a crisis about mathematical truth.
Right, wondering if the foundations were actually solid.
Exactly.
Yeah.
But this new AI crisis, it's a crisis about mathematical values.
Which is a huge distinction. A century ago, they were terrified that what they thought was true might actually be false.
Right.
Today, the truth of the math isn't the problem at all. An auto-formalized AI proof is objectively, verifiably true.
What's the issue?
What's under attack is the unwritten set of practices that make math a human endeavor. Like what we reward, what we consider a meaningful contribution, and what it actually means to understand a concept.
But wait, I have to push back here. Put yourself in the shoes of an engineer building these systems. If the AI outputs the correct answer, and it's mathematically sound, why does it matter if our quote-unquote values are challenged?
It's a fair question.
Like, if you prompt a model to design a bridge, and the bridge stays up, who cares how the AI arrived at the structural math? Isn't getting the correct output the entire goal?
Well, that assumes the goal of mathematics is solely to produce correct answers. Historically, no, it wasn't.
What was it then?
Tao explicitly maps this out. The goals of math were a tightly woven package. You had solving problems, building new theory, applying that knowledge to the real world, training the next generation, and even the aesthetic pursuit of elegance.
And they all moved together.
For centuries, yeah. These goals were perfectly aligned. You literally could not achieve one without achieving the others.
Because if you wanted to solve a notoriously hard problem, you had to invent a new technique.
Exactly. That technique built new theory, which you then used to train your students. Progress on one metric naturally dragged all the other metrics forward.
You solve the problem, you inevitably gain human understanding.
Right. And that historical alignment is exactly why Goodhart's law is so dangerous here.
Goodhart's law states that when a measure becomes a target, it ceases to be a good measure.
Spot on. And with generative AI, those goals are finally diverging. By treating the metric of solving a problem as the sole target for our AI systems, we decouple it from the rest of those historical goals.
Because the AI is inherently ungrounded. It doesn't actually care about understanding the theory.
Exactly. It's just optimizing for the appearance of a satisfactory output. It's a statistical engine predicting the next token, right?
Right. Unless we force it into specific logical constraints.
Yeah. And when you combine that underlying architecture with the financial incentives of the AI industry to just, hit benchmarkable achievements.
Like getting a gold medal on the Math Olympiad.
Oh, absolutely. The entire ecosystem optimizes purely for the singular metric of generating a correct solution. So the system is incentivized to just leave human comprehension behind.
Because comprehension doesn't boost your benchmark score.
Exactly.
It's exactly like training a reinforcement learning agent to win a video game.
Yes. I love this analogy.
The agent discovers some physics glitch in the game engine. It clips right through a wall and warps straight to the end screen in 3 seconds.
Right. Completely bypassing the level.
Exactly. It achieved the metric perfectly. It got the fastest time, but it learned absolutely nothing about the actual mechanics, the enemies, or the intended path of the game.
The AI is basically clipping through the wall of mathematical theory. It bypasses human intuition and just spits out the verified solution.
So to see where this glitch happens in the real world, Tao breaks down the day-to-day workflow of problem solving into 5 stages.
Right, starting with stage 1 and 2, solve and verify.
Because just generating a solution isn't enough, right? A prominent mathematician's inbox is already filled with unsolicited 100-page proofs of the Riemann hypothesis.
Yeah, from random people. Generation requires verification, and that's where autoformalization is moving so fast.
Translating natural language math into proof-assisted languages.
Exactly. Things like Lean, ROC, or HOL, it vastly accelerates the verification process.
And for anyone who hasn't used them, languages like Lean aren't like Python. They are strictly typed functional programming environments. They force every logical step down to fundamental axioms.
Right. So if the code compiles, the math is flawlessly true.
But that creates a completely new failure mode.
Yes. What happens when your system outputs a 50,000-line formal proof that compiles perfectly, but no human alive can read it?
Which is already happening.
Yeah.
If you look at the Erdu's problems database right now, there are AI-generated proofs just sitting there.
Yeah, totally unverified by human eye.
Right. The human experts who manage the database, even the researchers who prompted the AI in the first place, they openly admit they lack the capability to understand the logic.
It's wild. The machine says it's true, it compiles, but the human basically just has to take its word for it because the architecture of the thought process is so completely opaque.
It's a formally verified proof that literally no human being on the planet actually understands.
Which completely breaks stage 3 of the workflow, exposition.
The ability to clearly communicate the results so others can learn from it.
Exactly.
And this was honestly the most fascinating observation from the paper for me. Tao points out that when AI writes out a proof, the grammar is flawless, the formatting is pristine, but it totally lacks what he calls natural friction.
It's too smooth. It'll spend pages on trivial algebra and then gloss over a massive counterintuitive leap in logic.
Right. He included this amazing visual in the paper to prove this. It's a scan of a highly complex 1991 paper by the mathematician Jean Bourgain.
Oh, the one with the scribbles.
Yeah. A young Terence Tao annotated it with these frantic handwritten scribbles. They say things like, I hate Jean Bourgain, it's just AARGH.
With like 3 question marks next to a dense paragraph.
Exactly. But wait, as someone who writes code, I have to challenge this. We spend enormous amounts of engineering effort removing friction. We use linters. We write clean documentation. We hate spaghetti code.
Sure, yeah.
So why on earth would we want confusing, frustrating human writing in our research?
Because you have to separate noise from signal. A typo is noise. A compiler error is noise. But in advanced mathematics, structural friction is a massive signal.
How so?
Think about reading a human-authored pull request. You might notice the author suddenly becomes incredibly defensive or apologetic about a specific module. They rewrite a function 3 different ways.
I see.
That friction signals to you, the reader, that this specific module is dangerous. It tells you to slow down. That frustration Tao felt reading Bourgain, that was him wrestling with the mental model.
So the friction is actually the primary channel for transmitting tacit knowledge.
Exactly. AI over-polishes the text. It removes the typos, but it also sands away the structural friction.
So you have proofs that are, as Tao explicitly says, easy to read and hard to learn from.
Right. You verify every operator, but walk away with zero intuition for why it actually works.
And if humans can't learn from these frictionless proofs, the entire downstream pipeline just completely collapses.
Right. Which brings us to stages 4 and 5, community acceptance and canonicalization.
This is where the shift from proof scarcity to proof abundance really hits hard and causes that proof indigestion.
Yeah, because the peer review system, much like open source software maintenance, is built almost entirely on volunteer human labor.
Humans have to actually read the proof, digest the logic, and accept it. If AI is churning out novel, opaque proofs for $10 a pop, human peer review is going to drown.
It will be instantaneously overwhelmed. The bottleneck shifts from generation to digestion.
It's like having an incredibly powerful AI coding assistant submitting 10,000 pull requests a day to an open source repo.
Oh, that's a really great way to think about it.
Right, and every single PR contains millions of lines of perfectly compiling, totally bug-free code.
Right.
But it's entirely uncommented, logic-defying spaghetti code.
Right. The CI/CD pipeline gives it a green check mark because it compiles, but who actually reviews the PR?
Exactly. How does it ever become part of the core architecture if the human maintainers can't understand it?
It doesn't. You can never merge it because you can never maintain it. And in mathematics, merging that pull request is called canonicalization.
Which is putting a new result into its natural generality, connecting it to other theories, and packaging it into textbooks to be taught.
Right. And Tao emphasizes that canonicalization is the absolute slowest, most excruciatingly human-centric part of the entire pipeline.
It's basically immune to being optimized by an LLM.
Exactly. You are integrating raw data into the human web of understanding. If we flood the zone with undigestible AI proofs, canonicalization just halts.
The knowledge exists on a hard drive somewhere, verified by ROC or Lean, but it never actually enters the human mind.
The advancement of comprehension stagnates, even as the volume of solved problems goes exponential.
So how do you, as a working professional in AI or ML, actually adapt to this overwhelming new reality?
Well, Tao points to the 2026 Leiden Declaration on Artificial Intelligence in Mathematics. It lays out a few crucial shifts.
Which has some really practical steps, right?
Yeah. The baseline is transparent tool disclosure. You have to be totally upfront about when and how you use these tools. Covert AI use is the worst-case scenario.
And Tao actually models this beautifully himself. In the acknowledgments of this very paper, he explicitly lists how he used AI.
For literature searches, drafting diagrams,
Auto-completing sentences, and even reformatting his presentation slides into the paper itself.
he definitely practices what he preaches. But the declaration goes much deeper than just asking you to cite your tools. It demands a fundamental shift away from the theorem economy.
The theorem economy being our current prestige system, right?
Exactly. Right now, academia and industry heavily reward the person who generates the proof or achieves state-of-the-art on a benchmark. Being first is everything.
But in an era of proof abundance, generation is just a commodity. It's cheap.
Right. The true scarcity is digestion. We have to completely rewire our reward systems to value the grueling human work of exposition and canonicalization.
The person who successfully digests and explains a complex AI proof must be valued just as highly as the system that generated it.
Which brings us to the most practical, actionable takeaway in the entire paper. Tao proposes an ultimate rule of thumb for establishing human authorship in this new era.
You can think of it as the Chalkboard Test.
Yes. He says if the authors cannot convincingly demonstrate that they are able to give a clear, expert-level talk on their results.
And, answer unscripted questions about the mechanics of the work.
Right, exactly. If they can't do that, then the results simply should not be published. Period.
Even if the proof is formally verified by an AI system.
Yeah. If you, the human author, can't walk up to a chalkboard, draw out the architecture, explain the friction points, and communicate the why of the proof, it has to be viewed as an incomplete submission.
The human explanation is a hard dependency for publication. I absolutely love
This
that.
forces humanity back into the center of the process. The AI can do the heavy lifting, but it does not absolve the human of the responsibility of comprehension.
It's a massive perspective shift because the ultimate goal of your research, whether you're proving theorems, designing neural network architectures, or deploying software, it's not to hit an arbitrary metric on a dashboard.
Right. It's not just about bumping up a metric or generating a million lines of code.
Exactly. The goal is to help humans actually understand and think more clearly about the world.
You have to optimize for comprehension, not just output.
Totally. And that actually leaves us with a really provocative final thought to ponder, especially if you're an ML engineer training these exact models.
Oh, about the training data.
Yeah. Tao points out that the entire reason AI is currently succeeding at mathematics, the reason it can solve 7 out of 10 novel problems, is because it was trained on the canonical, human-digested theories of the past.
Right, that grueling, slow, friction-filled human canonicalization process. That is literally the training data your models rely on.
Exactly. So if we give in to proof abundance, and humans stop doing the slow, painful work of canonicalizing knowledge.
Because we're just addicted to AI warping us to the end screen.
Right. What happens to the training data of the future?
Wow. Will our models eventually starve themselves of the very human friction they need to learn?
It's a huge question, something you really have to explore and mull over as you're pushing these models forward. Keep digging.